So hi everyone. So today in this video I will be discussing a problem of graph theory which is based on the concept of binary search and DSU together. So this problem has been taken from the USACO official website. I will link it in the description. So the problem reads like this, that one of the farmer John's fields is particularly hilly and he wants to purchase a new tractor to drive around on it. The field is described by an n cross n matrix or grid consisting of non-negative integer elevations. A tractor capable of moving from one grid cell to an adjacent grid cell in 4 directions of height difference d cost exactly d units of money. Farmer John would like to pay enough for his tractor so that starting from some grid cell in his field, he can successfully drive the tractor around to visit at least half the grid cells in the field. So, if the number of total cells in the field is odd, he wants to visit at least half the cells rounded up. That is, we have to take the seal. Uh, so, our task is to compute the minimum cost necessary for buying the tractor capable of doing this task. Right. So, this is the input given, and the sample output should be 3. The input given to us is like the grid given to us is 0 0 0 3 3. So let me draw the grid first. So this is the grid given in the input, and we have to find the minimum cost for a tractor so that it will be able to visit more than half of the cells present in this grid. So this is a grid of 5 cross 5, right? There are 5 rows and also there are 5 columns. So this is a grid which is 5 cross 5. So total number of cells present in this grid is, total number of cells will be 5 cross 5, that is 25. So we have to visit at least half of the cells rounded up, right? That is, we have to take the seal. So what would be the seal value in this case? It should be 12.5 rounded up, that is 13. So we have to visit greater than or equal to 13 cells in this grid, right? So accordingly we have to choose a value of like the minimum cost of a tractor that is capable of visiting at least 13 cells, right? So how we will approach this problem? Let's see. If we want to move in 4 directions, that is the adjacent cells which are valid in dimensions. So here, from here we will be able to move to this cell, we will be able to move to this cell, right? Because their elevations are same, right? So these integers represent nothing but the elevations of this cell, right? It is like the elevation level of this cell is 0, the elevation level of this cell is 3, the elevation level of this cell is 9. So right, so if we want to move from this cell to this cell, then it will cost us the absolute difference between these two cells. So for here, to move here from here, it will cost us 0 rupees, right? 0 rupees, right? And similarly, if you want to move from here to here, it will cost us 3 rupees, right? Not rupees, but yeah, 3 units of money. Similarly, if you want to move from here to here, it should cost us, like the cost of the tractor will be 9. So suppose we choose a particular value, let's choose like 9. Suppose the cost of our tractor, right, cost of our tractor, suppose we choose it to be 9. Then if we choose it to be 9, then this tractor should be able to move between every adjacent cells whose difference is less than or equal to 9. Got it? So if it is 9, then we should be able to move from every cell to every other cell. If you see, like the maximum absolute difference present between any two adjacent cells in this grid is 9, and our tractor is capable of moving between any two adjacent cells if its absolute difference is less than or equal to k. The same thing is explained in the question. If the absolute difference is, like, if it will be able to move from one grid cell to adjacent grid cell if the height difference costs exactly d units of money. So if with a cost of 9 it is able to move from this cell to this cell, then it should also be able to move from this cell to this cell, right? So if we choose the cost of tractor to be 9, then we will be able to visit all the cells, like 25 out of 25 will be able to visit every cell. So this will be a valid answer, right? It is indeed a valid answer, right? It is a possible answer. But the question has stated that we have to minimize this cost, right? We do not want to visit every cell. Like the condition is only that we should have to visit more than the half cells, right? So here we have to visit at least 13 cells. We do not need to visit all the cells. So what if we have chose the cost of tractor as not 9 but rather 3? So what has happened, let's see. So if we chose the cost of tractor to be 3, then it should be able to move between every two adjacent cells, right? It should be able to move between every two adjacent cells whose absolute difference is 3. So if we choose 3, then our tractor will be able to move from this cell to this cell, right? Similarly, it will move from here to here. Similarly, it will be able to move from here to here, here to here, right? So I am marking every cell with which the cell will be able to be visited using this cost, right? So if I draw it a little neat and clean, then what we will observe is so ultimately using this cost of tractor 3 we will be able to visit these cells, shouldn't we? We will be able to visit all these cells because the maximum absolute difference that is allowed is 3. Like if the absolute difference between any two adjacent cells is 3 or less, right, 3 or less, then we should be able to visit. And in this component the difference is at max 3, so we will be able to visit all of these cells if we choose the cost to be equal to 3, right? So how many cells we are able to visit using this value? If you see, so we are able to visit a total of like 5 first row, then 5 second row, then 3 third row, then 2 fourth row, and 1 last row. So it is a total of 16, which is indeed greater than or equal to 13, and we wanted this. So this is also a valid answer, right? And for this question, if you see, the output given was sample output was 3 only, so this is our required answer, and we will not be able to do it, like we will not be able to minimize it further. So this is the most optimal answer, right? So what we did, if you see, let me explain it more clearly. So what we did is we chose a particular value initially and saw that if it is a valid answer or not, and if it is a valid answer then we wanted to minimize that value, right? So we shifted our domain to a lower region, right? So the best method to solve this will be using binary search. So how we will solve it using binary search, let me explain it here. So we will choose a lower value, let's say 0, and a higher value. This higher value will be the maximum absolute difference that is present between any two adjacent cells in the grid. So if you want to calculate the maximum absolute difference, you can calculate, but I will take it 1e9 for the time being, and I will set the result initially to be -1, and I will update this result according to the boolean value returned by the check function, whether the mid value is an acceptable answer or not, right? So suppose we calculated a mid value using this low and high. So I hope you know the formula how to calculate it. Like, it is given by low plus high minus low divided by 2, right? And we will run this condition until and unless our low is less than or equal to high, like a standard binary search, nothing fancy, right? So we will be checking if this mid value is okay. Like, if using this mid value, so what does this mid value represent? It represents the cost of the tractor, right? Nothing much. So using this mid value, if we are able to visit more than half of the cells in the field, Farmer John's field, if we are able to visit more than half of the cells, then this is a valid answer. So we will update our result equal to this mid, and we wanted to minimize our answer, right? So we will shift our domain towards the lower side. So we'll set high to be equal to mid -1, and if it is not the case, like this mid value is inappropriate to visit more than half of the cells, then we will do the opposite, like we will set low equal to mid +1, standard binary search operation, right? And after this is done, whatever the value of res will be there, like the result, so we will just have to print that result value. So our answer will be stored in the result value, right? So now the question is, how we'll be able to analyze whether using this mid value we are able to visit more than half of the cells or not. This is the question, and this is the crux of the problem. So now we have to find a way to see how we will be able to calculate the number of cells which we will be able to visit using this mid value, right? So if you see carefully, then what is this? We saw that using the value 3 we were able to visit this much of cells. So this is forming a component, like a separate individual component. This the members of this component shares a common property, and the common property is that the absolute difference between every two adjacent cell or any two adjacent cell is at max 3, right? So to calculate this, we will be using DSU, right? Disjoint set union will be the best fit to solve this particular sub problem. Using it, we will be able to calculate the total number of cells that this mid value can be able to visit for, right? So how we will use DSU here? So what we will be doing is, we will be visiting every cell in this matrix, right? We will be visiting every cell in this matrix, and for each cell we will be seeing in the 4 direction that if the absolute difference, like first we will see if it is a valid cell, and if it is a valid cell, that is it is present inside the matrix, then we will see if the absolute difference between these two adjacent cells, right, any two adjacent cells, is less than or equal to mid. If it is, then it means that we will be able to visit from this adjacent cell to this adjacent cell, or that two adjacent cells, right? So if this is true, that is the difference between the adjacent cells is less than or equal to mid, it means that using this mid value we will be able to move between these two adjacent cells. So what we will do is, using the union find function, we will unite these two cells, right? So if we are able to move, suppose we are taking these two cells, so initially every cell is an individual component in itself, right? Every cell will be an individual component in itself, right? Every cell will be an individual component in itself. So if we are able to move, suppose from this cell to this cell, then initially it is like this, and we saw that if we are able to move from this cell to this cell, then we will unite them together as a single component, right? So we will be doing this for every other cell, like every cell present in the matrix, if this condition satisfies. So what is the condition? The condition is simple, that if it is a valid cell, right? If it is a valid cell and the absolute difference between the values of these two adjacent cells is less than or equal to mid, it means that we should be able to move between these two adjacent cells. And if we are able to move between these two adjacent cells, then they should be present inside a single component. So we will unite them together using the union find function, right? So in this way, these much cells will be present inside a single component, and after that, at last it is done, what we will do is we will simply check the size of this component, or rather the size of the largest component that we obtained. So here the size of the largest component will be 16, right? The size of the largest component will be 16, which is greater than or equal to 13. And how we will find the size of the largest component, I will tell you that in the code, right? So this was the logic. So this was the logic behind this question. So like what we did, if I tell you from the beginning, so the question has asked to find the minimum value of the tractor. So so I told you to choose a mid value and then check if this mid value, using this mid value, we are able to visit more than half of the cells in the grid. And if we are, then we will update our result. We will update our result to this mid value and then change our domain to a lower region, otherwise to a higher region. And whatever the value of result will be there at the end, it will be our answer. Then the problem that came is how we will calculate the total number of cells that we will be able to visit using this mid value. So for that, I told you that we will be using the DSU disjoint set structure. Like we know that here a component is getting formed because they share a similar property, and the property was that the adjacent cells had a maximum absolute difference of here 3, right? In this, for this test case, it is 3. So any two adjacent cells any two adjacent cells, so for any two adjacent cells in which the absolute difference is less than or equal to mid, we will unite them together. Like we will be doing it for each cell through the 2 iterations, 2 for loops, and at the end we will check what is the largest size of the component that we obtained, right? So if the size of any component exceeds or becomes equal to the required value, what was the required value? It was this, like the seal of total cells, like the seal of the total half cells, right? So if it is true, then we will return a true, and it will be, and that is what was required. So I think now you got the approach. So let's get into the coding part. So we will take the input of n, and now we have to take the input of the matrix as well, right? After the input of the matrix has been done, let me declare it here also. So our input consists of a 2D vector, so I will do vector of vector long, and I will name it as field, right? So it consists of n cross n dimension, right? So initially I will give every cell value to be equal to 0, right? Okay. After this I will start my binary search operation. So I will set low to be equal to 0, I will set height to be equal to 1e9, I will set my result to be equal to -1 initially, and I will run this while my low is less than or equal to high, just a standard binary search concept, and I will calculate my mid value each time. With what is the formula for mid? It is equal to low plus high minus low divided by 2, and I will check if this using this mid value would be appropriate to visit more than half of the cells in this field, and if it is, then we will update our result to be equal to that mid, and we will shift our domain towards the lower side, right? Towards the lower side. Why? Because we wanted to minimize our value, so we'll say set our height to be equal to mid -1, otherwise it should be equal to low is equal to mid plus 1, and we will print the final value of the result, whatever comes. This will be our most optimal answer. So let me write down the check function. So what parameters will be passing? We have to pass mid, we have to pass the vector field. Don't forget to pass it through reference, right? Otherwise copy will be made continuously. Okay, sorry, it should be long. Okay, now as I said that for a particular mid value we will be using disjoint set union to see how many cells we are able to visit, and to connect adjacent cell using this disjoint set we will just see one condition, that if it is a valid cell and if the absolute difference between two adjacent cells are at most mid, right? So if it is, then we will unite this using the union find operation. So let me do that. So here I will declare a disjoint set, and it will consist of total n cross n size, right? It will be of n cross n size because we have to consider initially every cell to be an individual set, right? Initially it is in itself a component, so every cell initially is itself a component. So we have to pass down n also here. Let me do that quickly. Yes. So after disjoint set is initialized, so after the disjoint set is initialized, let me also copy down the standard code which is of disjoint set union. So this is the standard code for disjoint set union, supporting mainly two operations like the find ultimate parent, union by rank, union by size. So I will be using union by size, right? You can also use union by rank, but I will be using union by size. So after disjoint set ds is initialized, what is said that we have to visit every individual cell and see in its 4 direction that if there is an adjacent cell that we can visit using this mid value, right? So what will be the coordinates of this new adjacent cell? So new x will be equal to this original I plus IT0, and new y, that is the yth coordinate of this adjacent cell, will be equal to j plus IT of 1, right? So if our direction is defined as follows, so this is our direction vector. uh, the order of the movement will be like, first we will move towards left, then we'll move towards right, then we'll move towards top, then we'll move towards bottom, right? So accordingly the coordinates of new cell will be calculated, and if the coordinates of this new cell is valid, like valid condition is like this, like we have done this many times in DFS questions also. So if it is a valid cell and the absolute difference between the values of these two adjacent cells, that is field of nx and y minus field of ij, right? So if the absolute difference is less than or equal to whatever the mid we passed, then these two adjacent cells should be connected in our component. So like if you see, then the coordinates of these cells are like 0 0 0 1 0 2 0 3 0 4, right? But we wanted it to be like 0 1 2 3 4 5 6 7 8, like we wanted it to be like this, that 0 for this cell, first for this cell, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and so on. So how we will do this? So to do this we will use a simple mathematical formula or trick rather. So what will be so what is the formula here is, it will be equal to in plus j, in plus j for the first cell, and for the adjacent cell it will be nx into n plus j. So why this works, let me see, nx into n plus j, not j, it should be ny. So why this works, you see, suppose we want to calculate it for the first cell. So for the first cell we know that the coordinates are 0 0, so and n value is 5, right? So it will be 0 into 5 plus 0, which is equal to 0. So 0 will be assigned to the first cell, then to the second cell, like this cell, 0 comma 1 coordinate, it will be 0 into 5 plus 1, which is equal to 1. So 1 will be assigned to this cell. So suppose we want to check for any random cell, like suppose we have to check for this cell. So the coordinates for this cell is like, so the coordinates for this cell is 3 comma 2, right? 3 comma 2. So if we do 3 into 5, like I into n plus j, so what value we get? 3 5 to 15 plus 2 17. So it is the 17th cell if we start counting from the top, right? So 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17. So that's why this formula I into n plus j is correct in assigning values to each coordinate in the cell or in the matrix, right? So that's why I did this, like I into n plus j for the parent cell, and the neighboring cell that we are visiting, its coordinates are nx and ny, so nx into n plus ny. So after this is done, we want to find the size of the largest component, right? So like we will be visiting for every component and checking its size. So how we will check the size? We will be checking the size using this function size of component, right? That's why I have used union by size and not union by rank here, because I wanted to find the size of for each component, right? So we want to find the size of this component, and if this size is greater than or equal to, like the number of cells that we were able to visit using this mid value. So if the size of any component exceeds or becomes equal to a fixed value, right, then we will return a true, otherwise we will return a false. And what is this fixed value? So this fixed value is nothing but like the total half number of cells and its seal, right? So it will be equal to n into n, rather n into n plus 1 by 2. So if I explain you from the beginning, what we did was, so we wanted to find a suitable value, like the minimum value for which we will be able to visit more than half of the cells in the grid, right? So what is that required number? It is equal to fixed, like we want to visit at least fixed amount of cells, right? So we took the input and we applied binary search, we calculated a mid value and checked if using this mid value we are able to visit more than half of the cell. How we check this? We check this using the disjoint set data structure. Like if any two adjacent cells were sharing less than or equal to the mid value, the difference was less than or equal to mid, then we united them using the union by size operation. And after this was done, we just checked if the size of any component, like the size of any component was at least this fixed value, and if it is, then we return true, that is it is a possible answer. So after it has returned true, this is a possible answer, so we updated our result and we shifted our domain towards the minimum side because we wanted to minimize our answer, otherwise it would be equal to low equal to mid plus 1, and whatever the final value of result came, this is our most optimal answer, so we printed this. So now if I run up the code, so our expected answer was 3 and we are getting the input as 3. So let me submit this on the website itself to confirm the correctness of the solution. Right. So this was the question. Let me submit the file here. Okay, I forgot to do one thing, just a second. Like when you will be submitting the code on the USACO website, make sure this is not commented, like it should be in this format, right? And also make sure that the name of the question is same as this. So what was the name of the question? It was tractor, so I will name it tractor rather, right? So let me again submit this code. I think now it is fine, just a second. So now if you see, okay, so we are getting the correct output for every test case. So this was all about this problem. I hope you got the concept, like how this problem used binary search and DSU together to calculate the total number of valid components and update our answer accordingly, right? So that was it from my side today in this video. So if you have any doubt, feel free to comment in the comment section. I will try to help you out. Thank you.